So today is the fourth presentation in our scientific visualization workshop series, and we're hoping to do this at, beyond this semester, but here's the calendar for this semester. And things may happen, in like the November timeframe to move things around, but for the most part, at least especially for the next month or so, we're pretty fixed in the schedule. So next week, Chauncey Friend, who's one of our colleagues in the Advanced Visualization Lab, who's stationed at our Indianapolis facilities, and he'll be coming down or maybe presenting remotely. I haven't confirmed that with him. So he'll be talking about augmented reality for visualization. So we'll have kind of two things on immersive technologies back to back, and then we'll start. We'll talk about some other topics after that. All right. So today is immersive visualization or virtual reality for visualization, and a quick kind of statement about what we're talking about then is taking scientific visualization, which we've been talking about the last 3 weeks, kind of focused mostly on desktop tools, and apply that to what we call an immersive interface, which is just kind of a fancier way of saying virtual reality. So that's what we're going to talk about today. I wanted to show kind of quickly, and we'll see how this works, a quick demo of a VR application, or maybe a couple of quick demos to start us off, get us a feeling for what's going on. And so I'm going to bring up a little medium technology thing here. And, oh, I have to start photo booth again. Right. So just a moment. I have a camera set up so that the remote people can see what's going on as well. Oops. And had it set up, but then we crashed due to the, oops, lost it due to the crash. There we go. Oops, that's not what I wanted. Oh, here it is. All right. All right, so here's a camera looking at a computer which is showing us what's going on in a head-mounted display. So I have this head-mounted display, and this is one of the commercial tools that we'll kind of mention today. So one of the things we have is commercial tools and handwritten code. So here's one that does a molecular visualization. I haven't used this one too much. I've just kind of played around with it for a little bit. Joe here from Crane played around with it for 10 or 15 minutes before we got started today. So he's probably more of an expert at this than I am at the moment. But here's one application. So this is a commercial one. You can download it for free on Steam. And so it works both for commercial Vive and commercial Oculus tools. I won't try to demo that while talking. But I do also want to show one other application. If we can get out of here. And that is ParaView. All right. So we talked about ParaView 2 weeks ago. And so I want to just quickly show you how easy it is now to do ParaView. So one of the files we looked at 2 weeks ago was from Professor Horowitz. And so we'll bring up his data real quick. Load it in. There's the frame. If we add a contour to that, at the value we talked about back then, and apply that, we get this, I don't know what stage this, what stage is this, Dave? Okay, uniform density of neutrons. And so we'll add the connectivity filter, which we did the other day. All right, so I'm not going to play with the color or anything like that. But so this interface is backwards for those of you watching on the video, which is everybody, I guess. There's a button down here. It says send to OpenVR. So I just click on that button, and it gives me a little warning. And if I go to, whoop, I'll have to turn that down. My display mirror, here we go. It'll show me what's being shown in the Vive. And if I look at the right direction, there is the data. Oh, I was going to say it looks squished, but that's because there's a cutting plane on there. I'm going to put the head-mounted display on real quick here. So there's a cutting plane, and I can grab this cutting plane, and actually I can move that data so it's closer to me. I can fly around the data. I can grab the cutting plane, slice it through any way I want really quickly here. I can also grab the data and rotate that around however I want. So I can move the data relative to the cutting plane or move the cutting plane relative to the data. And so again, it's a pretty simple pair view thing. We can do more in pair view to get our data a different state. We can animate this one, although this one loads pretty slowly, does a lot of calculations, so it's not really pleasant to watch animated. But it works, and it works pretty quickly. So it it has some limitations in the speed if you're trying to do a lot of data, and we'll talk about that in a little bit. But otherwise, it's a commercial open source. Actually, it's an open source commercially supported package. And if you have a Vive or an Oculus, you just press the button and you're ready to go. So, so that's something we'll talk a little bit about those things, and we'll do demonstrations for those of you who are here with us. We'll do demonstrations later after basically we're done talking. And you can try pair view, you can try the NanoMe molecular viewer, or some of the other things that I'm going to show today. All right, oops, turn my volume down. I don't know what's going on. There we go. It went all the way down. Okay, so I need to get focus here. There we go. Maybe. There we go. All right, so this is a lecture series on scientific visualization. We haven't really talked about what virtual reality is, so I'm going to spend just a couple slides explaining what I mean when I talk about virtual reality. So here's a definition for virtual reality. That's a lot of words, so I'm going to break it down into some chewable segments. So the first thing is you want to know where the person is, because virtual reality responds to the movement of the person. So you have to, what we call, track the user. We have to know where they're at. The Vive has that built in. If for those of you in the room, you can see I'm pointing to, there's a couple of these stations. We call them lighthouses for the Vive, and they put out a pattern in the air of light, and then the Vive itself has these little dimples on it, and each of these dimples is sensing when that light pattern comes by, and that's how it knows where it's at. And the same is true for the controllers. Different virtual reality systems use different techniques. The Oculus uses cameras instead of the lighthouse, but works essentially similar concepts. So once we know where the user is, we want to display to the user from their perspective, right? So we want to augment their senses. Usually we're at least talking about vision. Sometimes we're talking sound and touch. And then finally, the goal is to put the person into that space, right? So we talk about being mentally immersed when I give my full lecture on VR, Intro to VR. Mental immersion is not necessarily a requirement of VR. It's the first two. It's the physical immersion that's more the requirement. But we want to make you feel like that everything makes sense to you, right? I mean, it doesn't make sense that you're standing in a molecule, but if you're able to manipulate the molecule, scale it, move atoms around, things like that, in a natural way, then we'll call that kind of being mentally immersed and making sense. There's three kind of major, or two major and one minor way we do that. One is to put the display on your head, which is what we're showing with the Vive here. One is to have a display that the user enters, so we call that cave or cave style. That's this middle picture here, and the middle picture. And so that works where there's screens on all sides of you, or several sides of you, and also on the floor. Although we can also do that, for example, on this screen that we're watching here in the room. It's a 4x4 tiled screen. If we want to just see something really large and kind of walk around things, we can do that as well. I've spent the last few days getting kind of a basic example running on this screen, which I can kind of fire up after we're done. It's not as impressive as the commercial VR that we're going to see. So, don't get your hopes up too high for that just yet. But we have a lot of different software that we can install, and that'll work out well too. All right. So our motivation then for bringing this virtual reality concept to scientific visualization. So I'll talk a little bit in a few slides about the demonstrated value of virtual reality as an interface of it being natural and people being able to use interfaces where 6 degrees, you can move things around. It's not like you're mapping a 2-dimensional mouse into a 3-dimensional world, and with rotations, it's even more controls. And then as we've been talking about this semester, visualization, we're looking at different tools, different ways of exploring science data. So we want to bring those two things together and make it even better, right? So we want to have, we're looking for then a kind of a suite of tools that we can have that'll allow us to explore our data with a natural user interface, right? You ready, Eric? I can get you that picture if you want. All right, so why do we want to do immersive visualization? So we just have some little bit of motivation, but I mentioned already that virtual reality gives you this natural interface with the world, so you can naturally explore the world. You can actually go inside your data, which in some cases may not make sense, but in some cases you want to be able to be there, be in the space, and look for relationships between things. And so, like I say, sometimes that makes sense, sometimes maybe it doesn't. One question then is, where does virtual reality fit in your scientific analysis workflow, right? So in general, there may be some exceptions, but in general, VR, when you go into a VR experience, you're not there to do the analysis. You're there to go and collect data, make observations that you can then just come back from. So I like to make it the analogy of going into the field. It's kind of like a field trip. At one of my past assignments, we had people who would go to Alaska and go to Antarctica and go to the desert and collect data, find things. And so often they would need to teach their new students who are working with them the lay of the land. And so one of the things you could do is give them a feel for the space before you go there. But that's just one example of what you might do. Really, you're there then to take some measurements, get some insights, and then come back to your office space, come back to your computer with your statistics packages and other analysis tools. And that's really where you're going to do most of your analysis, right? And in some cases, you might actually use it to be recon for an actual field trip, right? And so as I say, so one of the people I used to work with, he would take people to he would take students to Alaska. They needed to find a valley that had certain properties. And in order to figure this out, kind of get a sense ahead of time, they would actually bring it up in virtual reality and kind of look at some of the valleys and things like that. A lot easier to do now that we have Google Earth, but in the past they would actually rent helicopters, fly around, and that was kind of expensive. So virtual reality then for this whole process is more, I like to think of it more of a scientific instrument, right? So it's a place where you take measurements, like if you had a microscope, thinking to a kind of a basic standard I should say, a scientific instrument, and it lets you get different views of your data, right? So if you have a microscope, you're getting a different view of your data. And then you can also use it to enhance data. So sometimes the data is kind of messy. It takes kind of a human intuition to figure things out, but maybe that intuition is hard to bring about when you're only looking at it in 2 dimensions. If you can actually see it in 3 dimensions, you can see relationships between fibers or something like that, then you can make this data enhancement and cleaning task a lot easier. I'll show an example of that as we go on. Again, you can kind of take a tour of some data, right? So you can, if you already have a bunch of molecules and you want to show your students a bunch of different molecules, you can kind of take a tour of all those molecules. And then, as I've already mentioned a couple of times, you can actually do actual recon for an actual trip in the field, right? So now this doesn't necessarily apply to most of you unless you want to argue to your management that you want a bigger virtual reality facility. But one of the questions then is, for people who have VR facilities, is how much is that facility going to be used, right? So in a lot of cases in scientific spaces, the facility doesn't get used 24, or not even 24/7, but 8 by 5 even necessarily, right? 40 hours a week. And so that looks like kind of it's not being put to good use. But sometimes really the question is it being used enough where people are getting good benefit out of it, right? So it doesn't have to be used all the time unless of course you're doing something like training where you want the usage. If you're just trying to get people in there so that they see relationships, then they go back to their desk and then they make use of it. It's like if you have a microscope, your scientists don't have to be looking in microscopes, you know, all the time in order to be doing their science. They have to look, get some data, make some, try and deduce things, and then they go back and figure things out, right? So, so if you're arguing for a VR facility, even if it's not a big one like this, even if it's for a lab full of head-mounted displays, I like to use that as one of the arguments. Right, so one of the issues when we're dealing with scientific visualization in VR is that we tend to have a lot of data. And so if you're doing, you know, for VR for games and things like that, they basically reduce the amount of information they're presenting to the point where it renders fast. We may not have that luxury, or we may want to get to that luxury of having things render fast by having less data. We might want to see more or a good percentage of our data. And so we might suffer with lower quality rendering than the games do. So right now, if you're a game company and you want to sell your product on one of the VR stores, they basically require that your game run at 90 hertz or your product run at 90 hertz. And so that's, you know, a lot of processing. That's, I think that's about, I can't remember exactly, but about 11 milliseconds you have to do all your rendering. For a lot of, you have a lot of big scientific data set, you might not get to that point, right? You might have a much slower thing. Now, the slower you go, the worse the experience is kind of for your brain, right? It doesn't look as natural if it's going very slow. One of the benefits of having, of using like a screen like we have here, this tiled screen that we have, a big screen like that, is that you can get away with lower frame rates and not have your body sort of reject that and get nauseous from that, because it doesn't move around. It stays stable. It's you that's doing the moving. And so the images on the screen don't have to react as fast. If, on the other hand, you have a display on your head, when you turn your head, that has, you know, what you see has to change immediately. And so it's actually a lot more strenuous on your brain for the head-mounted display than it is for the cave-style displays. So if you're doing science and you have a big screen, you can get away with the frame rate being a little bit lower. Otherwise, you have to reduce your data, right? You have to reduce your data so that you're not seeing all of it. Maybe you're seeing a subsection where there's something important happening, or maybe you're just seeing it all sampled down. And so you can then do your exploring and then again go back to your desk. Or maybe once you've kind of perused your data at lower resolution, you can say, over there, in that corner of my data is where I'm really interested. Let's look at just that corner, but in higher resolution. All right, and so let's talk about then the cost, a little bit about immersive displays. So here's our kind of cave-style display that's up in Indianapolis now, just installed this year. And so it's another tiled display wall. It's about, it's twice as big as the one you're looking at, and it curves around, so you can have data on all sides of you. So that's kind of a big facility. It's going to be expensive. Again, if you have a need, you can argue for that. It'll help your science. But we also have now the commercial off-the-shelf VR that's priced pretty cheaply. The computer actually costs more than the display at this point. So you want to get a nice computer that costs, you know, $2,000 or $3,000 maybe. But then at some point, especially if you're doing custom code, really the main cost is the people doing the code development, the people processing the data. That's where a lot of your time is going to be. And so that's where, if you can save a lot of time in development by having a bigger display, you can also have a win there. All right, I said earlier that we talk a little bit about kind of demonstrated value of virtual reality. So I have here 4 research experiments done using virtual reality, starting back in 1990 by Fred Brooks. So in the Fred Brooks case, they have a molecular viewer. We'll see a picture of it later. It had a force feedback display, and they wanted to have 2 molecules dock with each other. And so they wanted to compare a desktop interface with that versus the virtual reality display. And they found that basically, I don't remember exactly what the task was, but the subjects in this task were basically able to perform twice as good, or twice as good using the VR display. A few years after that, at NCSA over in Illinois, we had a volume visualization tool, and we did similar kind of test. Can people in the on a desktop interface do the same, how well do they compare with a person using the Cave virtual reality interface. And they found, I don't remember the multiplier, but they also found that the virtual reality interface was better. Kenny Gruchala, who's now at the National Renewable Energy Lab, did a research project on figuring out paths for oil drilling. And so again, I don't remember the multiplier, but definitely the virtual reality had the bigger benefit. And the last one listed is Prabhat at Brown University, and he was looking at scientists, I don't remember the exact task, but they were looking at blood flow through arteries. So those are research papers, but there's also people who I think have just as kind of good a value who talk about specific cases where they had kind of a big win from virtual reality. So Gil Borer, who was at Duke at the time, he was just taking his friends, showing them their cave at Duke. He had some visualization of a forest canopy, and they were just having a conversation, looking at it, and then they something struck him, and this is one of the examples I talk about where you have this kind of eureka moment. You were only in the cave for 10 or 15 minutes having a conversation, you see some relationship, you go back, now you're doing statistical analysis with R or whatever, and so the rest of your work is sitting at your desk doing kind of traditional stuff. But it was that moment of insight that you got while you were in the cave. Oliver Krylos has a paper on several different scientists who've found benefit using caves at UC Davis. And then Gary Kinsland has a similar story to the one from Duke. And he was, again, he had his data in the cave because he had a relationship with the people who ran the cave at the University of Louisiana, Lafayette. And was again bringing a friend just to show him, hey, here's my data in the cave. And he had really kind of literally just finished a paper on this very data set. And while in the cave with his friend, he realized something that he totally missed in this other paper. And so he went back and he got a whole new publication just out of this one little insight that he got out of literally just being in the cave for 10 minutes. So these are the kind of things, this is, there's no published thing there, right? There's nothing, that's not a scientific study in and of itself, but that anecdote I think still lends credence to the value of virtual reality for visualization. All right, so I want to talk about kind of a quick tour of some tools that are available for doing visualization with virtual reality, and we'll talk about some examples as we go along. I've broken them down into kind of 3 categories. So one is a special purpose tool, right, where it was written just for this task. Another one is general purpose, where it's like ParaView, where we can load in lots of different kinds of data, and then we can just kind of output it to VR. And then the last one I call Shanghaied, which is basically where you have a computer graphics program that does a particular task. It's meant for the desktop, but there are some tools who can capture the rendering as it's on its way to the desktop. And as they capture that rendering, they send those polygons to a VR display, and then you can actually see the polygons in the VR display. There's some limitations to that. For the most part, the tool then doesn't even know it's being displayed in VR. So if it happens to think, well, they can't see this, I'll just throw this away. Whereas in virtual reality, you could turn around and see it. The application doesn't know that, and so it may have discarded some of the data. And also, there's not really going to be a good user interface for that, right? Because all the user interface is going to be on the desktop. None of that's going to make it to the VR. All right, so let's go through a little bit of examples. So here's some old stuff. So I talked about the Fred Brooks experiment. That was with this nano manipulator. And I mentioned, or I had on the slide, in the previous slide, this notion of custom applications. 20 years ago, of course, we didn't have off-the-shelf VR applications. We had to write everything pretty much ourselves. So there was a lot of effort, a lot of manpower, woman power put into doing that. And so we had to spend a lot of time, and it took a lot of time to get to the place where we had a tool that was usable. One of the goals then at that point was to use some of these general purpose visualization tools and add a module such that you could then do virtual reality with that, much like we just saw with ParaView at the beginning of today. And so these were some tools. I have pictures of those, so we'll see those in a minute. Here's this molecular docking application that I mentioned with the Fred Brooks study. And so this is at University of North Carolina. The haptics force arm came from Argonne National Lab. And so they were able to both see and kind of feel the molecular forces as they interacted. Here's one from NASA Ames where they're doing visualization of wind flow around a space shuttle. Kind of one of the unique things about this then is the old style VR display. So here's a head-based display, but you actually had to hold it to your head, kind of like you do with your phones now. And there's this arm here that is extending out. There's a counterweight out here because there's, you know, literally like little TVs inside this box here. It's not like we have our smartphone displays that we use today. So this box is pretty heavy, so it's not something you want to have to physically hold or wear on your head. And so there's an old display called the Boom. But the tracking was really good because it had mechanical tracking. Here's another one that I mentioned from Rachel Brady at the National Center for Supercomputing Applications. And so she has this volume visualization tool. Here's a chicken embryo. And I think this one is a horse fetlock. But anyway, one of the things I mentioned already is this notion that we can't see all of our data, right? And so the chicken embryo is sampled down data so that we can see the whole embryo there. But this other one, this horse fetlock or knee data, we're only seeing a portion of the data. And that's this notion where, well, we can kind of choose, right? We can see sampled down the whole data set, or we can find the data that we're really interested in and focus on that. And of course, 23 years ago, that was even, you know, more the case, even with a computer here that cost over $500,000, right? So just to do the rendering, we kind of made it so that you can only see a portion of the data, and that's what we're seeing with this square in the middle. And you can grab this square and move it around your data set to see different aspects of it. And there's tools. So one of the things that she was working with researchers who wanted to, say, measure paths through data, so perhaps the brain stem of this embryo. And so since it's kind of curly and it's a little fuzzy data, you could like drop these little breadcrumbs, which is where the name comes from, and drop them along the path here, and then at the end have it report the length of that, the length of that path. And so that was the task that she had and that she did in her study to find out whether people were better at it in virtual reality or not. Here's a quick one. Here's an atmospheric visualization. So this was a desktop tool, which with the source code, we could actually add some virtual reality into it. There's Los Angeles smog there. And then the general purpose tools that I talked about. So a lot of them, at least two of these have gone by the wayside, right? They're very popular for their time, but haven't survived. Actually, AVS may still be around, but I don't know anybody who uses it. But anyway, they have these tools where you connect things, and it was kind of like ParaView. ParaView does this internally. You have something that reads the data somewhere, something that processes it, adds color, you know, finds isosurface here, so our contours, and then feeds that to some renderer. Well, at the time, we were able to create a renderer that produced two side-by-side left and right views and lets you then interface with and the views changed based on the virtual reality system. And so here, again, you can take your desktop tool and bring it into virtual reality, much like we're doing with ParaView now, and see that. And then also, the visualization toolkit, which we'll talk about later in the semester, it's the web interface for that. But that was kind of a popular visualization, popular toolkit that had lots of visualization features, and you could connect together. You could trust kind of what it was doing, and lots of people were taking that and putting it into virtual reality. Nothing that kind of lasted because VTK itself was evolving, and so things would change and eventually it would break. But there's more to that story we'll talk about later. So here's some pictures of VTK from early days. All right, so those were some early examples. Now there's some modern examples. Again, here's a 3D visualizer. So this is earthquake data at the globe. Here you're actually standing inside the Earth and looking out to where the earthquake data is. You can generally see that it follows where these tectonic plates are. It does a lot of other things, though. It has slicing and isosurfacing, much like ParaView has and Streamlines. Another tool from UC Davis is a LiDAR visualization tool. Here we're just looking at points. So LiDAR systems generate, you know, literally billions of points, maybe hundreds of billions of points. And so even for modern computers with modern graphics cards, that's a lot of data. And so the researcher at UC Davis, Oliver Krylos, developed a system that loads in the data where you're looking, right? So it focuses in as you get closer to something, it fills in the points. So the computer doesn't have to render all those points at the same time. The one on the left has kind of an A/B sampling. So it's terrain from 2 different times of the year. and you can see where there's vegetation growth, and you can also see where maybe some landslides happened and or some building took place. And then the one on the right is from power line observations where power companies want to make sure that vegetation things aren't encroaching on their lines. Here's a Esri-based, so our ArcGIS-based visualization tool for a cave. Here's a volume visualization tool, which I want to show a little video of this one just to give you a sense for that. So let me break out to, oh, right, I lost my VLC. So let me start up VLC here. So yes, I'll talk about that in a little bit, but these last couple tools, the LiDAR one and the earthquake, the one that was showing earthquake data, and this one, they're written with a tool called VRUI, which at the moment, VRUI only works on basically Linux or Unix-based systems. So it'll work on a Mac. He has got it, and I've got it to work on in our lab over at 10th and the Bypass. He has gotten the Vive to work on Linux with his system. So we can look at these applications in our Vive. One of the things I noticed though, and other people have noticed, is that when you have that much data, you actually notice the resolution of the Vive isn't as good as you might imagine if you're just playing a game and you're just kind of concentrating on the game or some other stuff, or even a molecule. There's not that much data, and so the resolution doesn't bother you so much. But once you get to lots and lots of points, that's when the resolution actually starts to become noticeable. So, you know, the next generation of head-mount displays, I think, will probably address that to a degree. But yeah, so some of these tools, I'll talk about volume visualization at the end for Windows too, but some of these tools, the guy who authored the base toolkit is kind of a Linux guy, and so some of these are limited in that way. But we'll talk about different opportunities later. So let me show the video of this, which I lost my bookmark on that since my machine crashed. All right. So here's that same tool that we're seeing in the picture. Here's that tool in a cave, and so it has this interface. And one of the things we want to do is be able to kind of, in this particular case, is count the number of microbes or whatever. I can't remember exactly what this data is, but anyway, you would count the cell nuclei or something like that. And so normally the grad students would have to go and look at 2D slices and say, well, there's 10 on this slice, and then look at the next slice. Well, there's 12 on this slice, but 3 of them were still on that slice, and you have to figure out, which ones are which. Whereas in three-dimensional, you can kind of go and just kind of tag them, and you can do much better, more accurate job of counting the things, and also seeing, again, the relationship between things. And so here's the part of the user interface for that. There's a transfer function to convert the density of materials into different ways. Kind of a pretty nice utility for its time. So that's one tool that we actually have running over in our lab at 10th and the Bypass. I've lost my mouse. There it is. All right, so let's pause that. So anyway, so that's that tool in virtual reality or in motion. Here's another example. Oops, need my focus. Here's another example actually using the same tool. Here's a couple of researchers went to the Sahara Desert, and they want to see what are the wind patterns underneath. What were the prevailing winds 500 years ago over the Sahara, right? And you can tell that because as the prevailing winds change, the shapes of the dunes change. And so what they do is they go and they take this ground penetrating radar, and every meter they take a measurement, right? And they go through, and now it takes them a few days to make these measurements. We reshape that to the actual terrain, and then you can look underneath and see the shapes of these dunes over time. And then in virtual reality, as I said, you can use human intuition a little bit better. It's kind of hard maybe to have a computer automatically figure out, what are the angles of the dunes in various places, what kind of properties do you want to look for. Maybe with machine learning today, we could do a better job with computer. But back, 10 years ago, this is what we had. And so you could, with kind of the human's ability to deduce things, take measurements, and then again, once you have those measurements, take them back to your lab, and that's when you actually do your kind of analysis.
Were you guys involved with that project at all?
Yeah. So this would, well, when you say you guys, this is when I worked somewhere else.
Okay, okay.
Yes, at the Desert Research Institute. So in this case, they were researching a desert, which isn't always the case, but yeah. So here's one that I was not involved in. This is from UC San Diego, where they have several caves and different facilities. And so they have a program they call CalVR, and they were doing some archaeology. So they start with LiDAR data, which you can see here. And then as the ground is being dug away, they actually rescan it, and then they can like archive where they found different artifacts and have captures of that, and then be able to visit that in 3D. So you can go back in time, you know, pre-dig, levels of I don't know, unearthedness, and see how things were. Here's a similar tool. This is from the Supercomputer Center in Stuttgart, Germany. And so they do a lot of, he has a general purpose tool where you can bring in a lot of different types of data. It's kind of like ParaView, except features were added based on what the scientists he was working with wanted to do. Here's a picture related to the anecdote I talked about earlier with Gary Kinsland at the University of Louisiana Lafayette. And so this is, I don't know if this is the particular data that he was looking at when he had the insight, but one of the things they've done here is have these like what they call magic lenses. So they have some general data, and then inside these boxes they can see different versions of the data, and they can have those overlaid. And so you can kind of like cut away parts of it and see different things. You can tell this is an old picture because they actually use a CRT monitor. Here's another one I want to show in a video form. And so this is another one from UC Davis. And so this is one where she's looking at the surface of Mars and is looking for different rifts and different properties of different rifts. But specifically, you'll see that there's a picture of the researcher herself in here holding a little Wiimote. And the reason that this is kind of interesting is that you can then use this as an educational tool. So she was captured in VR, doing VR. I'm going to show you a video clip of it as a video, but it's actually stored totally three-dimensional. So you could look at her in 3 dimensions. You can actually be in VR while she's explaining things and see her, you know, inside the space with you. So let me go back to the movies here. Oops. There we go.
What infrastructure is required to have 2 people in the same model?
Right, so this is, she's captured with a Kinect, right? So $100 game device. So, and you know, that, the Kinect, I think the Kinect 2 is still out and you can still use it and still get it pretty cheaply. There are places that are using multiple Kinects to try and capture things. There's more sophisticated stuff. LiDAR systems, you know, capture a lot of points, but they're not really great at real time, right? Because they're spinning, and so so they kind of capture from the outside in as well. There are people doing video captures. So one of the technologies that does this that hasn't quite got to real time is this you've seen in football games and basketball games where they have you know, really interesting play, and they want to show you the dunk or whatever from multiple viewpoints. And so they take cameras, like 30-some cameras that are mounted around the stadium, around the assembly hall, and then they take that data, they crunch it, and now they can watch it, you know, kind of in 360 or move around, zoom in, zoom out. So that's not really real time. So when they do that, there's somebody actually operating. Oh, this is going to, you know, I think he's going to dunk it, right? So start recording and start processing. And then about 5 minutes later in the broadcast, they'll show you that video. But, you know, computers are getting faster, right? You know, algorithms getting better. So I think those kind of things will happen.
I guess I'm wondering really, if I've got somebody in another state in the same VR.
Right. Yeah, so, I mean, if you're good with this, here, let me just run the video. If you're good with, oh, so for the people listening remotely, the question was, what's kind of the state of,
I'm trying to figure out what infrastructure is required.
right.
2 people using, let's say, an HTC Vive, one in Florida and one in Indiana, both in the same environment.
Right.
And interacting with one another.
Right. So, yeah, that exists here with the Kinect tool. This tool that we have now, this particular tool runs in Linux. So you'd have to Linux both sides, but other people are doing it with other, other operating systems. Let me go and find this data though. All right, so here she is. Here's Mars, or that's actually the sun, it looks like. Right, so this is, you can see it's the Connect. She's talking. I don't have volume control on my laptop at the moment. Oh, there we go. It's on the big screen.
The different places.
Right. So this is, again, a video of her talking, explaining things. Let me jump ahead while she's actually interacting with the data. Right, so here's Mars. And so her hand is where, she's seeing it in virtual reality. She's in virtual reality doing this. She's seeing it that way. And so when she touches a certain point, she sees it from her perspective. We're just another person seeing it from our perspective, and the two perspectives match. And again, we're watching this in video, but I could also replay this in a head-mount display or a cave, and I could walk around to the other side of her. Now, the Kinect is only capturing, one side of her, but I could walk around to the other side. I don't have to have this particular point of view. I can kind of zoom in, and all this is captured and can be replayed in virtual reality. This is just a video replay of that. And so again, this same tool can be used to have people collaborate remotely as well. And it's not commercial grade quality at this point, but it's certainly workable. Right.
Can you interact with her and she's interacting with you?
No, so yeah, so the question is, can she interact with us as well? No, this is purely pre-recorded. This is her talking. If I stand over there, she's not gonna look at me. She's gonna look at where she was looking when she did this, right? And so I can move around, and I can pause her. So it's like, oh, I didn't hear what she said. I can rewind her. But in this case, she's not live. This is all pre-recorded, and it's more of an educational thing. But like we were saying, we can do back and forth and see each other in virtual reality as well, using basically the same technology. All right, so we'll pause that.
That's Vrui as well.
This is Vrui, yes. Yeah, if you see those menus that are like that, that's Vrui. All right, so here's ParaView. So ParaView has a couple of different stages for virtual reality. This is from a couple of years ago, maybe 4 or 5 years ago, where our lab teamed up with Idaho National Lab and Kitware, which is the company that does ParaView, and we wrote in a plugin to make it work in caves and walls and things like that. And so we could bring it into a system that already had VR running and make that work. We had kind of some rudimentary interface stuff that worked. Idaho National Lab was funding this, and so once they stopped funding it, we stopped developing the user interface for it. But it generally worked, and Idaho National Lab still uses it. Separately, and we'll see this in a little bit, the folks at Kitware started working on it for the head-mounted display and with the Vive and Oculus, and we already saw that running earlier. Here's VRMD, which is a molecular visualization tool. This picture is a little coarse, but you can see there's some molecule stuff going on there in the background. And again, it's a desktop tool, this time where VR was kind of added as a plug-in feature. So VRMD knows there's VR in there. You can map button presses on your controller to do certain things, start an animation playing, resize things, move things, turn various features on and off in the molecular visualization. And again, we'll revisit that one in a little bit. I mentioned earlier this Shanghai notion. So here's MATLAB working in VR, and MATLAB doesn't know it's displaying to VR here. So MATLAB is displaying to the desktop, and you can actually see that in this picture on the right. In the background here on this side screen, we're not doing VR, we're just showing MATLAB's desktop. And this data, as it's being rendered to this screen here, is grabbed, and then we take those polygons and we map them into virtual reality so we can actually then walk around that same data. And so that's a specific tool that was done for MATLAB by a researcher at Duke. There's some generic tools that do that from commercial companies. So Mechdyne, a company called Mechdyne sells a product called Conduit. A company called TechViz sells a product called TechViz, or TechViz XL, I guess. And so I call these generic in that the notion is you put this on your system anytime you're rendering graphics to your screen, you can capture that and bring that to your computer. The problem is there's a lot of little kind of fiddly stuff, whereas if you're rendering it in this particular way, it might not work, or if you're rendering it in another particular way, it might not work. So they actually customize how they capture the stuff and how they process it for particular applications. So it's not quite as generic as the concept makes you think it might be. All right, so that I'm calling those modern, but now let's talk about some really recent stuff. So here's that VTK again, and now VTK is kind of formally introduced and has the ability to run in VR. And here we've merged VR with VRUI, if you can recognize those menus. And so there's some viewers there's a volume viewer, there's a Moose viewer, which is a simulation product. And this is actually being integrated into VTK releases. So if you have VTK on VRUI, you can just make this work. Here's a program called Cephas, which was recently open sourced. So this guy right here, James Money, was in the Department of Defense, and he started working on it, but then he went to the Department of Energy and open sourced it when he was there, and so you can get that. And so this has basically time data, so it has LiDAR data, it has drone flyovers with cameras, which you can merge, and then you can have other data and stuff that you want to keep track of, and you can, again, go back and forth in time and look at your data at different points in time. All right, so I said we'd revisit VMD, so a couple of features. We saw VMD in the cave, that picture, but VMD has had some extra things added on where it works at head-mounted displays. And it does a couple of different things. One is VMD is kind of known for its high quality rendering. The problem, of course, is high quality rendering. You don't get that 90 frames a second that you want. And if you're doing huge molecules, so this, I think, I can't remember for sure, but I think this is an HIV molecule right here, which is just massive. And the processing for that, if you want it to kind of be semi-real time, in this case, the rendering happened in a cluster of graphics cards in California, and we could watch that here in Indiana or at VMD's home in Illinois. And what the program would do is render that as kind of a big rectangle meant to be wrapped onto a sphere. So it would render it, then in the head-mounted display, you were just looking at the inside of a sphere, and so you could kind of look around and see what was going on. If you wanted to move, you could move, but then it had to refigure out the sphere again. So it would actually get kind of grainy, and then it would get high resolution. So you could get kind of half and half. You can do a little compromise. You can have high resolution data processed somewhere, but if you wanted to actually kind of move your head side to side, you had to reprocess it. But if you just wanted to rotate your head and look around, then you were good. You could look in any direction. And we can get a sense of that. I'll show some movies I can play the movies on the laptop, or you can play it on your phone, or I can play it in a web browser. And so one of the things that came out of that is you can also do 360 rendering with VMD. And so you can make your own movie, pre-plan a flight, pre-plan some features to get turned on and off, have the simulation running, and then you can actually record that to a movie. And John Stone, the author of VMD, has put some up on YouTube where you can actually just watch that. And actually, let's see if that's still in my browser tab here. There's my Chrome thing there. There we go. All right, so this is oh, I lost it. All right, so I will go and just search it. It's just on YouTube. And if you search VMD, VMD 360, there it is. All right, and so here it is in 360 mode. And I can take my mouse then and rotate it around, right? So I can look in any direction. These are water molecules, these red and white things, and they are working their way through pores in a membrane, like a skin sort of thing. And then somewhere on here, if you happen to have a VR device, you can click on the VR device. If you have this on your phone, you don't have to use your mouse to look around. You can just use your phone to look around. And I can show you that after we're done talking here. So I'll just get out here. For those of you who are remotely viewing, I have a little phone viewer. So there's a little phone viewer that you can carry in your pocket and put your phone on it and just run up that same YouTube thing. Run YouTube on your phone and you can just kind of look around like it's a little head-mounted display, right? I'll show this oh, that's not on the camera. For those who are watching remotely, I'll show you later. So this, we can also watch that same video in VR. And so in VR, I can just kind of naturally in the head-mounted display, and I have that up and running too. So we have there's a YouTube app for the Vive, right, and on Steam VR, and you can just watch YouTube 360s in the Vive pretty easily. All right, so this is, I think, the HIV one. All right, we'll stop that. All right, so VMD, in addition to have that cave view, has these lower, consumer-oriented views as tools as well. All right, we've mentioned VRUI a couple times, and we already addressed this. So VRUI, as it was developed, was meant for cave-style VR, big screens. But as I mentioned earlier, the author of VRUI got it to work with Vives and earlier versions of the Oculuses on Linux. And so you can do VRUI stuff. Here's a point cloud data set of the Temple of Isis in Pompeii that's been excavated and recreated through photogrammetry, which we talked about last week. And so you can see that point cloud data set, and you have all the features of the VRUI interface in this in the head-mount display. Again, I mentioned that the resolution, when you're looking at this kind of data, the resolution becomes noticeable. All right, and then we're back to ParaView, where we started, where OpenVR is Valve's interface to the Vive. It also works with the Oculus interface. And basically, as I showed when we got started, you just start up ParaView, you tell it you want to do VR, you load up your pipeline, and you press the button, and you're doing VR. So really conveniently done. And I mentioned earlier the notion of volume visualization. That tool that I showed earlier was for Linux. There's some folks, the team at Idaho National Lab that we've been collaborating with. They've been looking at using Unity, which is a game engine, and works under Windows, of course, as well as OS X and Linux. But while it's meant for games, it has the ability to actually do OpenGL shaders in it. And with OpenGL shaders, there's a lot that you can do in there to manipulate data. And so they're developing a volume visualization tool inside a shader, which they then just use Unity as the kind of the shell to hold that. And since Unity already knows how to do VR, it all kind of works together. I contacted them a couple weeks ago. They're not ready to share it yet, so I don't have a running copy of this just yet. And then this is, we looked at this data 2 weeks ago when we were looking at ParaView. This is the globular cluster stuff from Professor Vesperini. So a couple of our team members took that data and made kind of a fun application of it in order to demonstrate it to kids at the Science Fest, right? And so this, if you go to this URL down here, you can actually run it again on your phone. Also, though, we can run it in the Vive, just like there's a program called Supermedium, which takes web-based VR spaces. So there's a programming interface called WebVR, which is like WebGL. It takes graphics and puts it on the web. It takes those graphics, adds VR to it, and there's a product called Supermedium, which will load those web pages and just let you watch them in the Vive. And so this is one of those web pages you can just watch in the Vive, and I can demonstrate that this afternoon as well. All right. So those are kind of the bulk of tools designed for scientific visualization. There's a handful of other commercial software that we could kind of make use of for visualization. So this one's called Prospect Pro. It's an architectural based tool. It'll load, though, any SketchUp data set. So if you had science data and you brought it into SketchUp, it'll load wavefront models. So if you had a molecule, you could load that in. And you can do annotations. And this one lets you share as well. So this one actually works across the network. So you can create what they call a meeting. Multiple people can join these meetings and all be in the same space. And they have these little crazy looking avatars here with the little kind of pinpoint sticks. And you can see where their hands are and where their heads are. And when you're in there, you can annotate. So over here in this leftmost image, these arrows and blue lines were drawn by people in the space. They're not part of the model. They're actually drawn there. And those are persistent. So if you create a meeting, that meeting and any annotations you have stay there. And then if you join that meeting later, as long as the person whose computer this is being hosted on is up, you can actually see those annotations from the past. Right, so it's not cloud-based. So it's on somebody's computer. and then they join in to that meeting. And then it goes, I mean, it goes through the company, Iris VR is the name of the company, and then they kind of connect you at that point.
Okay, so it's not on-prem.
I'd have to, I don't know, 100% the details on that. So that's my understanding, but I could be wrong. But I've tried it with like up to 3 sites at a time. And usually I start the meeting one first, but that may also be just from habit, right? Right. We can investigate that and try it out. We have Prospect Pro on this system, but I don't have it on the back one, so we can't do the collaboration. If you want to stay around long enough, I can install it back there, but we can look into this later too. Yeah, so Jeff is online. Jeff, the question was, although I can't hear Jeff, unfortunately. If you want to type in the chat message, Jeff, the question was, how do Prospect Pro share data? Is it like a cloud-based thing, or does it go through Iris VR? So let me see if I can start the chat up here somewhere for Zoom.
So you're saying you can't hear me?
I can hear you talking, Jeff, but I can't. It's so mute. It's so low. I can't hear what you're saying.
All right, I'll type it.
Something is screwy with my settings. And I can't find the share either. Actually, someone else, are you in the chat, Essen? All right, so Jeff, if you could answer that question in the chat space, Essen will tell us the answer. And if you have a question about the question, we can clarify. Another tool is called Gravity Sketch. So this is more, where you start with a blank slate and you start designing things. And it has tools to like mirror things and do smooth surfaces and create, primitive shapes. And so again, this is kind of more for, as I say, building stuff. Maybe if you want to just sketch out some things. I'm pretty sure this one is not a collaborative. So this would just be you. You could save the data and load it back, but it's not collaborative like Iris Pro, Prospect Pro is. Tilt Brush by Google is another kind of famous one. This one's continually being enhanced because people are actually starting to use this on a more regular basis, and so Google's been enhancing it. But it's really just a paint program with some fancy paint brushes. It does have the ability to mirror things and draw straight lines and things like that. And you can walk around. I can run Tilt Brush if anybody wants to see Tilt Brush later. And then finally, there's Google Earth, which, especially as I mentioned before, if you're going out into the literal field and you want to do some recon on that, Google Earth is a good way to do that, find out where different places are. And so that works pretty well. So so at this point, we can now do some demonstration. You can try things out. We have a Vive running up front. We have another Vive running in the back. And for a lot of things like the molecular viewer, the calc flow, I forgot to mention calc flow. That slide got lost, I guess, when my machine rebooted. So there's a couple of commercial products called, darn it. Well, actually, so there's some pictures of it here. So let me just talk to it here. So here's calc flow. Use the mouse. So this is a commercially based tool. You can get it in Steam VR, so run on your Rift and your Vive. And it shows different ways of doing like mathematical expressions, and it'll plot those out for you. The same company did this program called, and so this was a student project at the University of California, San Diego. They started this up, they put it on the Steam store and sold it for like $10. And from that, they decided to start a company. You can now download this for free. They've open sourced it. And then now they're working on this molecular viewer where you can see they're manipulating this DNA molecule, but it'll load basically any protein data bag molecule, and you can manipulate it. This one is collaborative as well, so multiple people can be joined in the same session and talk to each other and point out things to each other. Joe, who had to leave early today, I let him, he arrived early because he knew he was leaving early, so he actually did the little tutorial in this earlier today. So if anybody wants to try that out, we can see that too. So any questions before we go to the demos? The molecule, it's called Nanome. So it's Nanome. And I've heard it pronounced nanome as well, but I don't know how they pronounce it actually. So their company is nanome.ai, I think.
I guess one of my main questions is what are some standard data formats? Because that's the big thing. For years now, I keep seeing lots of great ways to work with VR,
Right.
but I rarely get any information about how can I get my data prepared.
Right.
I do work with Groovy, I do work with Unity, but I'm like still struggling how, you know, now you have more options on
Right.
how to do this. So where is the trend going?
Right. So the question was about, for those who remotely, the question was about standard data types that are available. And so there's several standards, right? For molecules, the protein data bank is kind of the main standard. So most molecular tools are going to be able to load PDB files. For LiDAR, for point clouds, there's LAS, which is a standard. And so Oliver's program, LiDAR Viewer, will take that and then pre-process it into his format. So for LiDAR Viewer as a special format, because he's loading in data and taking it back out again. But you can take standard data from LAS and or just ASCII comma separated values and process those into his format. And then you can actually take his data and go back the other way too if you want. If say you erase some stuff, you know, you go in there, you process it, you want to erase it, some data. Like if you did photogrammetry and you had some data points that you didn't want, you go in, delete the data points you don't want, save back the ones you do want, and then do the rest of the processing that way. And then for like ParaView, well, 2 weeks ago we saw a huge list, but really just kind of, you know, XYZ plots with data at each, you know, several bits of data at each thing, right?
Do they handle related data? No.
So there are a couple of tools which I didn't show you that haven't been developed in a while, but there is one, I can't remember the name of it, but basically is a point edge visualization tool, connectivity tool. Cannot remember the name of it, but there's a VRUI tool that does that.
Okay, well, no, I'm gonna be looking more and more into. I learned Linux by working with VRUI. So Oliver Kralos has like a lot of. He teaches his stuff pretty well too. So
Right.
if you want to get into VRUI, he has some good resources.
Yeah.
There, so I recommend it.
Right. So for those who remotely, a recommendation for VRUI.
Yeah.
Essen, yeah.
Jeff responded, he says Prospect does not store data centrally, so the user
Here, I'll give you the microphone.
creates a workspace. So I'm going to relay Jeff's response to the question. The Prospect apparently does not store the data centrally. So a user who wants to collaborate with others creates a workspace, and all the data is shared with the participants, and they have to copy that data locally so that everyone has a copy of the data, and they collaborate on that data using the local apps on their machines. And apparently there's some desktop app it works at Prospect.
Right, there's a desktop interface, yeah.
Yep.
So if someone doesn't have VR, they can still participate in the meetings. So, okay, good.
A tool to really,
What's that?
they need to have the data locally done.
Right, yeah, so you have to ship the data around. And so I didn't say, so in it, kind of an answer back to his question about data type. So Prospect Pro will load kind of standard architecture stuff, Revit. It'll also load Sketchfab or SketchUp. I'm not familiar with that one, but step files, Jeff, Prospect Pro.
Maybe it'll run Revit, I'm sure it'll upload and stuff.
Right. Yeah, it has a couple of different formats that it loads, yeah.
But it's not a singular public data that everybody is logging into.
Right, no, it sounds like you're responsible for sharing the data on different machines. I guess I should have remembered that because I did that myself. He says what? Rhino. Yeah. So, but they are actually adding, I mean, they just added a new file format, I think, a month or two ago. So, you know, they're addressing, it's a licensed software, so you're paying for that one, so you can get some customer support, you know, out of that and tell them what you want, right? So anything Rhino can load, okay, which includes STEP, I guess. All right, any other questions? Otherwise, we'll go and do the demos and we'll stop our recording. All right, very good. And so next week is augmented reality and visualization, and Chauncey Friend will be presenting that. All right.